Okay, good evening, friends, and thanks for joining in. And the agenda for today's meet is to do revision towards Anthem quiz for large language models. And how we will approach it, we will basically take the PYQs and solve every PYQ question and understand the concept behind it. Thereafter, we will take the GAs. So week 11, week 12, week 9 and 10 didn't have any GA, week 7 and 8. And then while discussing them, we will also discuss the concepts behind them. Is that okay? And I will request everyone to participate in the discussion. So because it is, learning from each other and sharing the knowledge. And so it will not be a single monologue. I will request everyone to participate. With that, I have shared my screen. Is it visible to all of you?
Yes, it's visible.
Yes, yes. Okay. So we start here with the LLM. So this is the PYQ, the QDB3 PDF. So this is one paper available. Unfortunately, we had only one LLM term. So what was that term? Does anybody remember for that? So we go with the term quiz. It was available in the last term, na, LLM?
I think Jantum.
Chantum. Okay, let me check. It was. hmm, It is not showing in this term. Are you sure it was in Gentum?
Not sure.
Okay, let me try another one. What was that? Just now I did the bookmark. History. Alright. Yes, this is the one from here. Okay. This is a very good site in case okay, you want to prepare. So you go to practice and term, and here you can select LLM, and immediately it will tell you which term. So it was in April 2024. So we are opening that only April 2024. And what was the question number? UDB3, for example. To this, we can search it with this question. UDB3. Okay. Okay. So we will take one question paper from afternoon and one from forenoon. There are some different questions, so that's why we'll take one from forenoon and one from afternoon. Okay. Is it visible now to everyone? Shall we start?
Yes, sir.
Yes.
Okay. Thank you. Thank you. So first question is what is GPT? Okay. So GPT, and I will open a new document so that we. Okay, so what is GPT? So in one question paper, they have asked for GPT. So GPT is what? Okay? Can anybody remember? It is
Generate a pre-trained models.
generative. Okay, so like CLM, okay, it is generating and pre-trained model. And in the other question paper, they have asked about the BERT. Okay, so what is BERT? Okay? BERT is bidirectional because it take from both the directions, and E is encoder. It is encoder model only. R is the representations, and pre-trained transformer. Sorry about my loop. Representations from transformer. From transformer. Does anybody remember about BART? Okay? Part also can come.
Autoregressive something, right?
Yes. So bidirectional, and it is only auto-regressive
Transformers.
transformers. Okay. And there was another one, some this T5. So T5 is
Text
text
to
to text, 5 T's, transform and transformer. Okay, in case they ask these kind of questions. And then there was another one, C4. So that was colossal, a very big one, clean and crawled. And what was last C? Does anybody remember? Okay, we'll see that again. Okay, so this is a simple question, and consider an attention matrix of this. So this we had discussion on the WhatsApp group also, and how we found out. So suppose we implement a block-wise sparse attention mechanism by multiplying attention matrix. So here is they contain 4 identity blocks, and using approach, what is the computational complexity of the self-attention module? So we saw that if we do full attention, then the complexity is how much again? It
OT
is
square.
OT square. So this is full attention, and here only we'll cover the concept of block attention also, how it is done. So in the block attention, what do we do? That the sequence is divided into blocks. So for example, if we take this example only, that 4 blocks, so Q which will be there, Q will be, for example, T is equal to 16. So from 0 to 4, 5 to 9, and then 10 to 0 to 4, 16, sorry, my mistake. So it will be 0 to 3, 0 to 3, 4 to 7, 8 to 11, and some here 12 to 15, 12, 13, 14, 15. Okay, so this is Q1, this is Q2, this is Q3, this is Q4. And K is also divided into blocks. So here also I will have K1, K2, K3, and K4. Now, when we say pi, for example, there was a question in the GA. If I say 0 to 1, 3, so it means this is the value of K. The Q remains same. So here it will become Q1. This is K0 is K1. This is Q2. This is K3. This is Q3. This is K2. This is Q4. And this is K4. So here the attention when you pay, it is in blocks. So Q1 is paying attention to K1. So here is the first block of attention. Q2 is paying attention to K3. So here is the attention. Q3 is paying attention to K2. So this is the attention. And last one is the Q4, K4. So this is the, and how do we do it again? That for different heads, we have got different schema of this. So now with this, we understand this question that again, there are 4 identity blocks, and we are doing the attention, and how your complexity will be now here. So if I'm not wrong, sorry, for the full attention, your complexity is T square D. Is that okay? Because you are doing multiplication of T into D into D into T, Q and K. Is that correct?
Yes, sir.
Okay. Now, when you do with this block attention, so what you are doing, this T which was there, it has been divided into 4 parts. And this is T into 4 parts. So in one attention, you are doing, this length is full T. Okay? This is this is T by 4. So here it will interact, we take one only. So it will interact here only. So this is how much? T square by 4. Is that okay? The second will be t square by 4. Third is t square by 4. And 4 is, sorry, this is t square by 16. T square by 16, t square by 16, and t square by 16. So your complexity or the number of multiplications and additions there of the complexity of t square, if you add them, this will become t square by 4. Is that okay?
Yeah, this is the complexity, right? T square by 4, you are saying.
T square is the 4 here. And in the question, what they're asking? They're asking computational complexity.
So no, T square 4 is computational complexity.
Yes,
Right?
yes. So computation, when we take, okay, we remove the constant.
Yeah.
So this
yeah.
will become OT square.
Mhm.
Okay, so this is the answer. And while doing so, we have understood these concepts also, how we do the blocks. Okay, so if this kind of question comes like the GA, they give you, for example, this kind of diagram, and they ask what is the where Q4 has interacted with which K, so we can answer that. Is this clear to everyone?
But in the lecture, the complexity for block attention was given OT square by C into D, right? So shouldn't we keep it OT square by 4, though it's constant over there, linearly increasing?
If I'm not wrong, your OCTD was OCTD.
Mm.
This was for your when you are using a local attention.
Okay.
Okay, so when you use the local attention, or there was another word, okay, when you are, this is a normal local attention, and the second one was dilated local attention. And in dilated local attention also, your C remains the same, but where you are paying attention, it becomes different. For example, here, it might pay attention to these two. But for both, C is equal to 3, here also C is equal to 3. And for this local attention and dilated local attention, your computational complexity is CTD. Is that okay?
Got it.
Yeah. Okay.
It should be t square by 16, right? Not t square by 4.
If you add on all this, so this we had calculated for one, second,
Okay, okay. We
third.
need to add all
Yeah.
this. Okay, got it. Fine.
Okay. Now we go to another question. So this is correct. Okay, this is the question. So first we understand what is the intent, okay, what they're checking. Suppose we pre-train a model using a text-to-text framework. So text-to-text framework was T5. That in encoder, okay, we are giving text, and then in the decoder we get text. Text in, text out. A user wants to fine-tune the pre-trained model on a regression task where the inputs are sentences but the labels are real value. And the label values ranges from 0.202 with a step size of 0.1. Given this, choose the correct statement. So statements they have given that objective function should be modified. The objective function of the pre-trained model need not be modified. Text-to-text framework cannot be used for any regression problem. We need to add a layer on top of the output layer that outputs a real value. So we have to understand that in the text in, text out, we can feed text in and we can take text out. And this, if we see, this is like that we have got only how many choices, okay, we will have from 0.1, 0.2, 0.3, 0.4 up to 2. So this can be considered as a text also. Is that correct? It is not a continuous value.
Yes.
So therefore, the objective function does not need any modification.
Okay.
Okay, so that is correct. Okay, the second option which is there, that is the correct option. That the objective function of the pre-trained model need not be modified during fine-tuning.
So if it was written that there is no step size, like it is continuous from 0.12 up to 2.0,
Okay.
then can it be used, or should the objective function be
Then
modified?
your objective function, remember that this text to text which is there, it will have a definite walkup size. Whatever you are doing, your text out might be having walkup size of 37,000, for example. Over that only it will have the your probabilities. Whereas if you take from 0.1 to 2, and if you take continuous values, there can be many continuous values depending on the precision. So your text in, text out, can it be used for this kind of thing where you have got continuous?
No.
No, I
No,
think.
no. Okay, so third option will be correct in that
Okay.
scenario.
Sir, can you explain it again, please?
Yeah, okay. So how do we do the text in, text out? We feed a text in, and so we are giving text in and we are getting text out. Okay. So this text out which is there, it is having some walkup size.
Yeah.
So it can only predict here text over a walkup size.
Mm.
Okay. Now in this question they said that your output is from 0.1 to 2 with a step size of 0.1.
Yeah.
Okay, so I can have here the values which are there. I can make this 0.1, 0.2, 0.3, 0.4 up to 2, and I can consider this as a text out. And when I'm training, I know that for this text in, my answer should have been 0.1. So I will like do the loss. I can have the objective function, same objective function. So in the text out, okay, what we take summation of L and Y at.
Mm.
Okay, so I can use without changing the objective function. I can use for this also.
Mm.
Now the question from Shubham was that in case this was from 0.1 to 2 and it is a continuous, then can we use text in, text out? This walkup size will always be definite. Any number, for example, you take for example 40,000,
Mm.
it can predict only those 40,000 things.
Yeah.
Whereas from 0.1 to 2, if I take a precision of 0.001, 0.0002, then up to 2, the values might be more than 40,000.
Yeah.
So then I cannot use this text in, text out.
You could use it, right? Because the it's just like your model is predicting more. Your model have more labels.
No,
Is that
no.
it?
We have to understand the objective function. See, if my walkup size is 40,000, for example, then it can have only 40,000 values, na, here.
Mm-hmm.
Out of these 40,000, only something will come.
Right.
Now, if I'm using for continuous and I want a precision of, for example, I want to predict like a 0.0001.
Mm.
So I have to, if I see from 0.0001 to 2, with this precision, these values will be more than 40,000.
Mm.
It means I cannot have this objective function here.
Okay. Okay.
Okay, understood? Okay,
Good.
thank you. Okay, now we go to this question, for example, and we will. This question is from BPE. Okay, byte pair encoding algorithm, and base vocabulary contains from A to Z and digits from 0 to 9. The rest of the tokens are learned from the dataset. So before taking on this question, we can cover the basics also of BP. How do you do BP? So for example, your three words are there and I'm directly taking it from your quiz 2. Sweeter, 5, uh, cleaner, for example, 4, and any other word like this. Does anybody remember this question? Okay, so we take these two only, for example, and I have to build I have to do byte pair encoding. So first, what step we do? We write all the unique words S, W, E, T, R, K, N. How many times S has come? 5 and delta W. So sorry, this is the word stop. So S is 5, W is 5, E, 5 into 3, 15, T is 5, R is 5, delta W is 5, K is 4 times. Now this E will come here, 4 into 3, 12. and n is 4 times, and r will become pi plus 4, and this will become 4. So this is your initial vocabulary when you build. So question might come that tell the numbers of tokens in the initial vocab. So how many tokens are there? 1, 2, 3, 4, 5, 6, 7, 8. So in this example, this is 8. Now in every merge again, now after this what we do? Now we do the byte pair encoding. And how do we do that? Now we find the pairs of the bytes. So here we will start from here. So SW 5, WE 5, EE 5, ET 5, TE 5, ER 5, R and W full stop is 5. Now we come to KE 4. This is EE. So EE is already there. It will get added here. 5 plus 4, 9. EN 4. NE 4. ER is already there. So it will become 5 plus 4. And this will become RW is already there. So this will also become 5 plus 4, 9. So how do we do the merge? So now we will do the merge. So these are my initial vocab. So I will write as W E T R K N, and W would have come here. Okay, and W. So this is my initial vocab. So here I check which is the maximum occurrence, and I check again from the starting in this direction. So it comes EE. So EE will be added here, and from E, initial number of E was 27. Now I subtract this 9 from here. So this will become now 18. Is that okay?
Okay.
Okay. And now number of tokens are how many now? 9. Okay. So remember in BPE, with every merge, one new token is formed. Okay. And in case, for example, this E value was here 9 only, and you subtract 9. So this E will remain in the vocab, though its value has become 0. Is that okay? Clear? Any doubt in this again? Anyone?
No, thank you.
So very good. So now what they have given, that this is the V, and this is V, and this is something. Assume that input text is normalized before applying pre-tokenization. It means that all these have become in the smaller cases. Enter the number of tokens returned by the tokenizer. Ignore the special token used to represent the boundary of the word W token. So they have asked us to ignore this W. Now, how do we do it? I will just copy from here.
Sir, how is the token UNK learned from means?
If okay, for example, why we have got U and K? Okay. So see, your vocab is, for example, this much only. And now a new word comes which does not have any token. For example, it has come sweetie. So is Y there? Okay? How you will do the tokenization of that?
Okay, so it will be mapped to UNK.
UN. Okay, that's a UNK step. So I will. Okay, now we see the steps. Okay, how do we do it? So what happens? It happens in iterations, in passes. So first something we break into all the characters. Now this will pass through this vocab which is there first time. So when it will pass through first time, what he will encounter first? It will encounter IN first. Okay. So in the first pass will become SOMETHING. Okay. And in the second pass when it will come, it will encounter ING. So it will come SONG. N E.
Shouldn't it encode TH first?
TH.
Yes, yes. INTH. You're right. TH has become, and then it will become ING. So number of tokens. Okay. Anything else here? Nothing is
Uh,
there.
just one second. The second part,
Oh,
does it have to be ING? It should be ING, right?
no, no. In the third person maybe, or
Oh,
this
this is the
second.
third merge. Okay.
Third person. Okay. Okay. So you just remember here, this ET has not come.
Hmm.
Okay. So your number of tokens are how much? 1, 2, 3, 4, 5, and 6. Is that clear to everyone?
Got it. Yeah.
Yeah. Okay.
But sir, the something S is capital, right?
That's why they have written that when we do the tokenization, you do the normalization first.
Okay.
Okay.
It's there, right? Okay.
Yes. Okay. Okay. And we go to.
Sir, actually, I had a doubt in that 9 or 18. What I was thinking is, so if we are counting pair, EE pair, so
Yes.
so like pair-wise it is coming EE, but individually if we count, it's like two E's in one token, na? So like if we are going to subtract, should we do it from 9 or 18?
Just hold on. Just hold on. Just hold on. I have opened, I think, wrong. Yeah. Okay. So here EE is 9 times okay?
Yes, pair-wise.
Okay.
Like pair
Pairwise.
has occurred 9
Pairwise.
times,
Okay. And here E was how much time? Okay. How many times?
like
27.
27.
So if okay, for example, I will just give you an example. If it would have been, for example, ER, for
Hmm.
example, and ER was, for example, 10 times.
Hmm.
First of all, now this you will deduct from both the tokens, from E also and for R also.
Yes, yes, yes.
Okay. So
Hmm.
in this case, yeah, it was only E. So for example, if E value was, and now definitely E and R will be greater than 10,
Hmm. Hmm.
then only. And for example, this was 18 and this was 12. So now you will
Okay.
deduct okay, this ER number which has come 10, it will become 8, and this will become
Okay.
2.
Ah, true.
Okay.
Correct. Hmm.
So that same thing I had explained earlier also. Okay. And one important point to remember here that though if the value becomes 0 also, then also that token is retained. Okay.
Hmm. Hmm. That's
Okay.
that's fine. That's
So
fine.
for example, we can see in this example also that IN and ING, now ING would have
Hmm.
been formed okay, from IN,
Huh.
but IN has been retained.
Hmm. Hmm. Hmm.
Okay, and with every merge, new token. So we can have a formula that number of tokens
Hmm.
after n merges is equal to initial token size plus n.
Okay.
Okay, if they ask you that after
Hmm.
after 20 merges, what is the token
Hmm.
size? So straight away we can find out.
Yes. Okay.
Yeah. Okay. Okay, we go to the next question then. Okay, so this we have done. This we have understood. Now we come to this here. So this is the question, and this is also from the GA. This is basically greedy algorithm, which we had used. So how to solve these kind of questions straight away. So this is your vocab. Assume that we have a pre-trained GPT model for text generation, and the first input token to the model is always the spatial token start. So here is start, first token. The prediction probabilities output by the model are given below. So we know for the start. Okay. Now we want to know which kind of algo it is using. The zeroth row of the matrix is the output probability distribution by the model given the special start token as an input. Following the greedy search decoding. So greedy search, what it does, it will always select the maximum. So in this case, it is 0.41. And how to map it? Okay, we can easily map all these to these. Okay. Start is here, waiting is here, is here, incredible is here, something is here, somewhere to be known and end. So here first keyword we will get 0.41, which is for something. Now this something will be given in this here, and now maximum is how much? 0.43. So here it will come 0.43, which is somewhere. Somewhere. So now next step we give somewhere. Now here the maximum is how much? 0.29. So we get 0.29 incredible. We give now incredible here. Now incredible is maximum is 0.48. Is it is. We give is here. Now we find what is the maximum is 0.29. 0.29 is waiting. And now we give waiting. Now here the maximum is 2, 3. Waiting, so it is 2, 3, 2. So your text generation which will be generated will be something somewhere incredible is waiting to. Is it okay?
Hello.
Yeah, got it.
Yeah, I think it is for B. 0.23 is for B.
Okay. Sorry. B. Okay. And here in this question which was there, this was discussed on discourse, and they accepted that the answer is incorrect here, because when we see the other paper, in other paper the same question is there, and there instead of waiting we have got B. Okay.
Got it.
Yeah. Now we come to this question. So now if this question in this only in this here, for example, if they would have given, for example, K sampling, then what will be the answer? Or any other algo? Then answer would have been -1.
Mhm.
Okay.
But what if they give like k equals to 2 and then you go about it? Yeah, k equals to 1 would be following greedy search, right?
K is equal to 1 is the greedy.
Greedy
But
search.
yes, but if K is equal to 2 also, then also you might not get, because you
Okay,
don't know
got
whether it will take 0.43 or it will
Mhm.
take the next highest 0.10.
Got it.
Okay.
So how did it got -1? Can you elaborate?
-1, because with the K sampling K is equal to 2, we cannot give the answer, na? Because see how many combinations will be there. Start, it can give 2.
Right.
Now if we select this token, it can give 2.
Mm-hmm.
This can give 2.
Yeah, it will keep increasing. Yeah.
Okay, it will keep on increasing. You can find the possible ones. Okay, if they give you a small, for example, if they give you only 3 rows and they ask you that can this text be generated by K is equal to 2, then we can do the exercise.
Okay.
Okay. Yeah. Okay, next question is, suppose a GPT model is pre-trained using the causal language modeling objective and fine-tuned on the summarization task. The context length of T of the model was kept at 2048 during both pre-training and fine-tuning. Assume that the model uses absolute position embedding with learnable parameters. Okay, so now what is the question? So now we have pre-trained it. So now a user runs inference on the model n times with an input text that contains 712 tokens, including the spatial start token. Then which of the following could be the possible length of summarized text? So the options are here. So this 2048 is the only one which is incorrect. Now what is happening? We have trained a GPT model which is a decoder only model. So and it has 2048 context length was there. So I'm passing 2048 tokens and I'm getting 2048 and text summarization. So we have pre-trained on all the summarization tasks. Now during inference, my first token has to be start, then only it will start, and the last token which is there, it is end. So effectively, how many tokens it can generate? If it has been trained on 2048, 2048 minus 1, 2047.
Shouldn't it be 2046? Start and end.
Yes, yes, it can generate any. No. Start take a token which is there. You are feeding these many tokens, and this is the summary you are getting.
Okay.
So you are
Including
getting.
special.
So you can get a summary only up to 2047 only.
Yeah,
So
it
that's
can't generate a start token, is it?
huh?
It can't generate a start token.
No,
That's
no, it is not generating. It cannot can generate this 2048 token, which is end. Okay. Yeah. So that is the basic logic there. Okay. Now this is a question of. So a user runs inference on a model n times with an input text that contains 712 tokens, including the spatial start token. However, the user observed that in each run, the model is generating the exact same summary. Based on this observation, select the decoding strategy. So if we see the case sampling, they don't work, okay? And by varying the temperature also, we get different outputs. So only the grading decoding strategy and beam search with beam size case greater than 2, we will get the same output. Okay. So these are the only two. Any question on this? Any discussion on this?
No.
Okay. Okay. Now we come to this.
And in that question, can we say like we are generating just the summary, so we don't need any kind of creativity in that. So we can go with that deterministic approach, and like the method that we are using right now is greedy and beam search, which is a part of deterministic, not stochastic. So can it be the reason?
Uh, See, the thing is like that, that during inference, like, I don't, you are right, okay, it is deterministic. That also is there. But for example, they would not have given you that it is a summarization task. It is just generating. You are feeding a text and you are just generating. But every time you are getting the same text output. So it means either okay, you are having the greedy algo or you are having beam search with k is equal to 2 because they only can give the same output at every instant.
Hmm.
Okay.
Hmm.
Yeah. Now this is a question. They have given this. Consider the encoder layer of a vanilla transformer. This is the all the parameters which are there. Parameters in the input and output layers. The input and output embeddings are shared. Okay, in this, the model uses absolute position APE using fixed sinusoidal encoding scheme. So there is no learnable here. And in this question, suppose suppose the number of encoder layers is n is equal to 3. What is the total number of learnable parameters, including the parameters of the input and position embedding layers in the model? Enter the final answer in 1000. For example, if this is this, then answer is like this. So shall we go through the basics okay, of the encoder decoder first okay, before solving this?
Yeah, sure.
Okay,
Yes.
and I'll give a hack also. So this is encoder and this is a decoder. Okay. Now in encoder, what are the parameters? So in encoder, first parameter starts with the embedding matrix. Embedding matrix, the size of embedding matrix is walk-up size into D model. Then we come to MHA. MHA, you don't have to remember anything, just use this formula 4 into D into D. Okay. And then you come to, after MHA, there is a layer now.
FFN.
First, there is a layer now. So after MHA also you apply layer, na?
So
So
why it
this
is 4 into D into D?
4 into D, WQ, WK, WV, and WO.
Okay.
This is D into
Okay.
D, this is D into
Okay,
D.
we are considering WO. Okay, D
And
mod into DQ. Okay,
yes, and
fine. And
irrespective of your number of heads, okay, this remains the same.
okay, okay,
Okay.
but we have to multiply it by the number of heads, right? If
No,
it's
no. That's why I'm saying that okay, if you have got number of heads, okay, for example,
mm-hmm,
if your D model, for example, was 64
mm-hmm,
and you had 8 heads,
mm-hmm,
so every head will, what will be the dimension of every head? 64 into 8.
true. Hmm.
Okay. And
Hmm.
when you add them, so it will become 8 into 64 into 8. So this becomes 64 into 64 only finally. So
Okay.
without caring about the number of heads, just okay.
So we will be having query key value, all three things in the head, right? So for each we are going to have this dimension.
D into D is your final dimension, which is coming for WQ, WK, WV, and WO.
Okay.
Now,
Hmm.
if you're for number of parameters, I'm saying that your number of
Huh.
parameters when you have got different heads, though you will be having different WQ, W
Okay.
dash Q, W dash dash Q, for example, if you take
Okay.
4 heads, but your
Hmm.
number of parameters when you will add them
Hmm.
for WQ,
Hmm.
WQ that, okay, that will become D into D only.
Okay. Hmm. Hmm.
Okay. And
Right.
when we take for all
Hmm.
Q, WQ, WK, WV, and WO, it is
Hmm.
4 into D into D.
Okay.
Okay.
Okay. Fine.
It's 1 minute. Divyansh, if you want, you can refer quiz one revision session. At that time, he derived
Okay.
everything and
Sure.
explained well. Yeah.
Sure. Sure. Sure.
Okay, so now we are going logically. So when we go to the encoder, first we encounter the embedding matrix, then we encounter MHA, then we apply layer norm after MHA, its parameters is 2D, then we go to FFN. So FFN, remember, formula is 2 into FFN into D plus FFN if bias is there. If bias is there. Else, it is equal to 2 into FFN into D without bias. Okay, that makes sense. And then after FFN, again we apply the layer norm and it is again 2D. So your total parameters which are there is you add okay, all this, you will get for the encoder. Is that okay?
Wouldn't it be D only, layer normalizations?
In the layer normalization, okay, you use the bias also.
Bias also. If it's not biased, if the question.
Then it is D.
Okay.
Yes. Because but in the layer norm, generally you use that alpha and beta.
Hmm.
Okay.
Got it.
Now we come to the decoder. Now decoder, remember everything is same except two things. Now this we start from here. So we get MHCA first. So MHCA has got 4 into D into D.
Hmm.
Then after MHCA we will apply layer norm. So it is 2D. Then we go to MHA. It is 4 into D into D. Then again we apply layer norm here 2D. Then we go to FFN. Formula remains the same. FFN as encoder. And then again layer we apply. So this is also 2D. And now finally output layer. Output layer is same as embedding layer. Parameters as same. Now it will become D model D into walkup size. And here will be the target walkup size. And this is the input walkup size. For example, if it was English to Hindi translation, then English might be having walkup size of 37,000 and Hindi might be having only 20,000. Is that okay? So using these concepts, okay, we can find the number of parameters. Now with this approach, okay, shall we solve this question? And this is for one layer. And as you have more number of layers, okay, then you multiply by the layer. So here only the problem in this question is that it is asking including the parameters of the input and the position embedding layers in the model, learnable parameters. Position embedding layer, which is there having sinusoidal fixed, okay, so there is no parameter for this. So there can be only embedding layer. Second, they are saying that input and output embeddings are shared. Okay, so it means output layer and input layer of the encoder and decoder which are there is only one P because they are being shared. They are same. Okay. Now we go. So this is an encoder layer of a vanilla transformer. So we start with the number of parameters and they are asking to include everything. So first here we come to embedding layer. Now embedding layer, do we see here any walk-up size? Walk-up size they have not given.
Yeah.
Okay. So here it is V, just write down V into, and they have given only T. Embedding dimension D is D model. So this become 256. Now we come to MHA. MHA will become 4 into D, 256 into 256. Now layer norm of MHA will become 2 into 256. Now we come to this, we have disregarded because we have taken the combined formula. FFN, they have given DFF is equal to 1024. So FFN will become, and have they given bias or no bias?
Bias is set to consider.
They have given bias.
Parameters.
Okay.
Like the parameters in the FFN
The
layer
parameters
comprise
in the
both.
feed forward layer comprise both weights and biases. Okay, so this will become 2 into 1024 into 256 plus 1024 plus 256. And then layer norm is 2 into 256. But due to this error, we cannot find because the walk-up size is not there. Is that okay? And they have especially given that what is the total number of learnable parameters, including the parameters of the input. If they would have given that, exclude that, then we could have calculated all this. Okay, so that's why this question has gotten error.
But embedding dimension is given, right? D embed.
Huh?
D embed has given, right? D embed equal to 256.
So shall we take this again, same 256?
I'm just asking.
No, we can calculate this. Okay. Can somebody help me in this? Calculate this.
Okay.
So 256 is 2 to power 8 into 2 to power 8 plus this is 2 to power 2 into 2 to power 16 plus 2 to power 9 plus 2 into 2 to power 10 into 2 to power 8 plus 2 to power 10 plus 2 to power 8 plus 2 into 2 to power 8. It is like this.
By the way, what's the vocab size here?
That's not given.
Walk-up size, just we are taking this D embed.
Okay.
It's 2 power 18, right? 16 plus 2, 18.
Which one?
Second term. 2 square into 2 power 16.
18.
This is 16. The second part I'm saying.
This is 16, 256 into 256.
That is 2 power 16, fine. The
Just
next one, 2 power 17, it must be 2
this
power
will
18.
become 2 to power 18.
Yeah, correct.
Plus 2 power 9, 2 to power 9, this will become 2 into 2 power 8. 2 to 2 to power 8 will become 2 to power 10. This will become 2 to power 19 plus 2 to power 10 plus 2 to power 8. Can somebody quickly use the Desmos for this? So we have got 8, 10, 2 to power 10 plus 2 to power 10 twice it has become. So this will become 2 to power 11. Let me use 8, 11, 16, 18, 19.
2 to power 81, right?
Huh?
2 to power 81.
2 to power?
81, I guess I'm.
No, this is plus, na? This is not multiplication.
Oh, sorry.
Yeah. 2 to power 8. Yeah. So let's use this. This we are getting, is this correct? 854, and now there are 3 layers. 2562 we are getting answer. Let's check what is the answer given in this. 2566. So have we missed anything, or we have done any error somewhere?
I guess some calculation will put up.
Huh?
The doc.
Okay, we can check that. Okay, but these are the steps. Okay, we have understood. Okay, these steps.
Also, one question: if there was position encoding which was not fixed, it should be T into T model, right?
See, the positional encoding will depend on the clipping also.
Clipping also, yes.
Okay, because okay, your clipping is also there. So just okay, shall we cover the positional encoding some basics? Okay.
Yeah,
Yeah.
sure.
Okay. So for example, I have got a T that lazy brown fox jumped over river. So this is my T. T is equal to lazy brown fox jumped over river. And embedding, for example, T is equal to, for example, we are just taking one example, D is equal to 4. So in normal sinusoidal, does it happen? So first we have the embedding matrix. Embedding matrix, which is V into D model. And when we do this, so we will get lazy. I'm just giving some example. This might not be correct. So this is the initial embedding. It will have, so brown will have 0, 1, 1, 1. For example, I'm just taking fox 1, 0, 1, 1, jumped 1, 1, 0, 1 over 1, 0, 0, 1 river. 0, 0, 0, 1. So this is the embedding matrix which is there, which we call X.
Mhm.
Okay. And when we do the sinusoidal, how do we do that? We write the position of this. So pause okay, starts from 0. 0, 1, 2, 3, 4, 5. Now for every this pause, we find the sinusoidal. So this is lazy and pause is equal to 0. So formula is sine of
Sine cos.
10,000 divided by 2i by d. Okay. And cos okay, this, and I is equal to t minus 1 by 2 or something like that. T minus 1 by 2 or t by 2. So in this case, I will become okay, 0 and 1. So for lazy will become, so this is all 0 sine. So this will become sine 0, cos 0, sine 0 and cos 0. And then, for example, we find about fox. So this will become sine of 1, 10,000, 0 is sine 1 ho jayega. Here it will become cos of 1. Here it will become sine of 1, 10,000, 2 by 4. And this will become cos of 1 by 10,000, 2 by 4. Is that okay? So we find okay, all this for all the 6-second tokens. And then whatever the values are coming, we add those values to these embedding matrices.
So basically, positions are the rows, sorry, the columns, and the I's are the rows, right? Like something like that.
See, J is I is like this, and
Mhm.
post is like this.
Okay. So lazy ka, that's why it's at zero position.
Yes. Okay. Now this will be post is equal to 1. So this is the basic sinusoidal and this is fixed here. Now this does not depend upon the now this lazy. So any second sequence when it will come, it will have 6 tokens only. So
Mhm.
your this positional encoding which is there, it remains the same. And the positional encoding, the size is T into D.
Mhm.
Okay. Now we come to relative positional encoding, for example. Now APE, when they said it had two parts, one was fixed and one was learnable.
Yeah.
Okay, so you were right, okay, that if we learn it, we don't make it fixed, okay, then size will be T into D.
Got it.
Okay. Now how do we do the RPE? So RPE, we write down the same thing now. The lazy brown fox jumped over river. And we write here also to find the relative brown fox jumped over river. So here we find the distances between them. So this is 0, 1, 2, 3, 4, 5. Here it will become -1. So this is j and this is I and this is j minus I. Okay. 1, 2, 3, 4. -1, -2, 0, 1, 2, 3. -1, -2. Sorry. -2, -1, -3, -2, -1. 1, 0, 1, 2. -2, -1, 0, 1. And this will be -5, -4, -3, -2, -1, 0. So see here, okay, the p values, these are the p values. So you can say that p0, p1. So
Mhm.
these are the p values. So here I will have p, these values from t minus 1 to minus t minus 1. So effectively I've got from 5 to -5 including 0. So there are 11. Now all these p's which are there, now they are calculated. So I will find P0, P1, P2, P3, P4, P5 up to P minus 5.
Mhm.
And now this number 0, this which is there, this becomes pos.
Okay.
3, 4, 5, 1, -1, -2, -3, -4, -5. And now I use the same sign, cos, sine, cos. And this D remains the same.
Got it.
Okay. So here again, now I'll find this. Now, if I'm doing attention mechanism, for example, between brown and fox, then I will use P minus 1.
P minus one. Okay. Position.
Okay, so that's how it gives the information. And second concept, okay, what they said, that if you do this, now for every xi, what you are doing, you are finding hi is equal to xi plus summation of all these pis, pjs.
Mhm.
Okay, so in for every hi, you are doing t summations.
Yeah. Yeah.
Then you do for all HTs, so again T summations. So here it becomes OT square. And now to reduce this, they covered that instead of doing this, you can do this summation when you are doing the attention score. Because your final attention score, which we are calculating, was H into, it was Q into KV.
Yeah.
Q we can write H into WQ, and K was H into HI, HJ, EIJ, HJ into WK transpose, and this is nothing but XI plus PI into WQ, and this will become XJ plus PJ into WK transpose. And then they said that this xi and xj, this will become xi wq into wk transpose xj transpose. Only this is the relevant term, and the last is the relevant term pi wq wk transpose pj. Okay, so this again, two terms which are there, they don't have any correlation. So at attention score, if you have got this PIPJ or P, you can say PIJ. So you add okay, this at attention score time. So by this okay, you can reduce this OT square. But remember in the RPE, this addition which is there, we do headwise and not layer wise. Second important point is that when you are doing here, you have to do at the time of V also when you are calculating V. So V is your this E which you calculate EV, and again you have got a PIJ which is V. So you keep like a two PIJs which are they are learnable as per Shaw. Is that okay? And in the T5, what they did, they said, Bola, we will only add a bias to this X, W, Q, W, K, this T, X, J, which is there. We will have a bias which is a scalar because this E, I, J, which is there, it is a scalar. And this scalar was learnable.
Yes.
Now, when we came to alibi means absolute okay, linear bias. So they said that instead of this, we will have only this xzt. Here I will have a fixed constant value. Sorry, fixed value. And how this fixed value was calculated? They calculated, they had a mass kind of thing and plus m, which m value was decreasing as per geometrically 2 to power 5. Okay, so these are the concepts of this. Okay, shall we move to second question?
Yes.
I will encourage everyone to solve this question. Maybe we did some mistake in the calculation, and please post on WhatsApp, okay, if you get the correct answer. Okay, otherwise I can show you I had got the correct answer. Okay, so our steps, okay, we should remember. Okay, now this second question is there. Any doubt, okay, till now? Anybody wants to contribute, okay, something in addition, please, okay?
Okay, so you got the correct answer is 2566.
Okay, so my calculation was wrong.
I'm just asking, I tried, but I didn't get.
Okay, okay. Take it.
Like even in the discourse, people are not getting that answer.
Yeah, the answer is very low compared to the number of parameters ka dimensions. I don't think the
Because
answer
it
is
is in it is in thousands, na?
yeah, it's in thousands. No, it's in like but the parameters, if we multiply any of the parameters, it goes up till like
Yeah, but okay, you know what is the reason behind that? Because they have kept okay, this V embed okay, D embed which is there only is 256.
yeah.
Whereas in actual cases, your walk-up size, for example, in your T5, it was 37,000.
Hmm.
So your maximum number of parameters in a model, they come from embedding layer and the output layer.
Yeah.
Okay. And what they did, okay, they are sharing also in this case, in this example.
Makes sense.
Yeah. Okay. Now suppose we increase the context length from T to 256 to T512, keeping the number of layers same. How many parameters does the model need to learn additionally? So this is straight away that T does not have any role in D in parameters.
Okay.
Okay. So there is a case 0. Okay. Everywhere we saw it is V walk-up size into D, D into D, 2 into D, DFF into D, 2 into D. This is the encoder part. For decoder part, you can write down for MHA plus MHCA 8 into D into D. All the layer norms is equal to 6 into D. DFF into T is 2, and this will become 2 into DFF into D plus D plus DFF. Okay, so this is the only difference. So anywhere do we see T here in the parameters? So T does not play any role in the number of learnable parameters, other than if they give a PE learnable. Only there T will play a role.
Oh, one thing in GA1, okay.
Yeah.
So the input embedding, so parameters, T was considered. It was batch size into T into D model. Is in that concept, T was taken as the input embedding
No,
there.
no. We will see that question also later. But if we see the all the parameters which are there in encoder and decoder,
Hmm.
do we see T anywhere?
No.
Okay, so T does not play any role in the learnable parameters other than except I have told you that in case again they gave P which is learnable, AP, only in that case your T will play a role. Okay. Okay. Shall we move to the next question?
Yeah.
Yeah. Okay, this is a question of a vocabulary contains four words: coffee, drink, I, often, and these are the embeddings. Assume that no position information is added to the embedding of excuse me parameters in the attention are WQ, WK, WV, WO. Suppose the input sentence is I drink coffee often. The corresponding attention matrix is equal to softmax of this is given below. Answer the following questions. So let's see what is the question. Compute the representation for the word often and enter the sum of elements in it. So what is the representation when we see the formulas? Okay, all formulas which are there. First we calculate this A has been given to us and your representation panel which we get Z is equal to
A into V.
A into V. Okay. Now this A which is there, where is often? Often will be here. It is I drink coffee often. So only for often, only this row is applicable to me. But only I have to what I have to calculate? I have to calculate V now. So first I have to make the embedding matrix. So embedding matrix for I drink coffee often. I drink coffee often. So I is here 1 minus 1. Drink is 0, 1. Then coffee is at first place 1, 0. And this is 1, 1. Therefore, V is equal to 1 minus 1, 0, 1, 1, 0, 1, 1 into WV. WV is 0.1, 1, 1, 0.5. So this will get 0.1 minus 1 minus 0.9. This is 0.5. This is 1. This is 0.5. This is 0.1. This is 1. And this is 1.1. And this will become 1.5. This is okay. So this is my V. And now I multiply this A into this. So I'm interested only this part, okay, from where I will get this representation part, okay. Representation will come in the last, okay, last row.
Hold on.
Okay. So can somebody do this multiplication part, okay? Or
Just a minute.
0.06, 0.45, 0.15, 0.35, 0.22, 0.13. So we don't have to do the entire part, okay? We want, okay, the last row only. So last row we will get, okay, from here.
Hmm.
Okay, so it will become 0.04 and they have asked, okay, enter the sum. So into minus 0.9 plus 0.12 into 1 plus 0.17 into 0.1 plus 0.67 into 1.1, and the second term is 0.04 into 0.5 and 12 into 0.5 to 1 plus 0.67 into 1.5. And if you add them, okay, you'll get the correct answer. Okay.
Yes, just open it.
Yeah. If I'm not wrong, I calculated it. It came some 2.08 or something, and answer given is 2 to 2.1. So simple mathematics only. We have to remember what is the representation, what is the meaning, and this often okay, which is there, it will come in last okay. So representation one we will get again. We'll get okay, 4 into 2 matrix. So this will be for I drink coffee often. So often is the last one. So that's why we have calculated only this row. Okay, is that clear, everyone? Yeah.
Yes.
Shall we move to section?
0.08 something. Yeah.
Okay. Next question is: suppose the input sentence is coffee I drink often. Then what is the attention score between the word coffee with often? So now remember that whatever the combination of the words, the attention score between those words, okay, it remains the same. Okay, often might come here and coffee might go there, but the attention score which is there, it will remain the same. So we can see what is the attention score between the word coffee with often. So here in attention score, coffee with often is 0.53. This will not change. Okay, and it was covered in the lecture also in the attention score. That this attention scores which you get, now you keep on jumbling these words in the sequence, the attention score will remain the same. So it will remain same 0.53. Is that clear? Can we go ahead, okay, with the next question? Am I audible?
Yeah.
Yeah. Okay. No. We move to next question then. Okay. Consider a GPT model trained using causal language model (CLM). The matrix below shows the elements of QKT in the first layer of the model. This is the QKT one, and what you're asking, what is the input length that would have generated this? What is the input sequence length what that would have generated it? So if they are asking T. So now we know the dimension of this QKT is T into T.
Yeah.
Q is T into D and K is D into T. We get T into T. So straight away from here we can get 1, 2, this is 8 because this is a 8 into 8 matrix. Is that okay? And now second follow-on question is that suppose the dimension of the value vector dv is 32, then which of the following could be the dimensions of the key and query vectors? So they have given some values and only we have to check that the dk and dq, they have to be of the same size.
Yeah.
Okay, so all the same size ones are the correct options. Incorrect are the where the sizes are wrong. Okay, so again, it has come from the concepts only. Now we can now follow on this question on this only, that suppose we pass QKT through softmax function this to compute the final attention score following zero based indexing at the time step T3, the attention score for the Q3 is highest for which one? So in this again, the concept what they have asked and what we have to remember that this is QKT, and in the CLM model, what happens that every step again we are doing masking. So
Yeah.
t is equal to 0, t is equal to 1, t is equal to 2, t is equal to, for example, t1, 2, 3, 2, 3, 4, 5, 6, 7, and 8. So we do like this again, if you remember. These are masked okay words. So here I will not pay any attention to these words. Is that okay? So at t is equal to 3, t is equal to 3, for example, if I take t is equal to 0, 1, 2, 3 here, t is equal to 3, then where is the Q3? This is the Q3.
Yeah.
Okay, and where which k he has got the maximum? So okay, sorry, this here t is starting from 1. T does not start from 0. 1, 2, 3. So this is the third time step. So here, if you see, what will be the value for this? K value, sorry, again I have 1. So this 2.26 is the highest okay? So this is the Q and this is K, K0, K1, K2. So K2 is giving the highest value.
2.29 not? Is it
2.26.
2.29 is masked?
Huh?
Like the next beside value I'm asking.
Just hold on, just hold on. So let's put the mask here. Now confusion in this is the T only, that T from where it is starting. Can somebody say it again? T starts from 0 or T starts from 1? Because the question is that in which row. So this is
It's
very well. This
it's
is very.
zero based indexing, right? So it
This is
should be
very clear that this is the. This we can strike it off. This we can strike it off straight away. So these are the attentions. So if we take, for example, zero based 1, 2, 3. So these are the values here. Now, where is the Q3? It is asking is attention score for Q3. Now here, what will be the Q3 value will be here available?
so highest will be for K 0, 1, 2, 3, K3, right?
Here K3 is coming now, right? But how do we say that this is for Q3?
Means the indexing, right?
It is the indexing. So K, let's check the answer. What's the answer in this? K is 3. Right, exactly. Okay. Okay, so this is the K value. So there, so we have to remember that we have to do the masking at every step here. So when we are doing Q1, K1, Q1, K1 pays attention to only K1. Q1, Q2, K2, it is paying attention to both Q1 and Q2, K2. And here it will 2.29 is the highest, which is coming from zero based indexing 3. Okay. Shall we go to the next question then? Any discussion on this again? Anybody?
No.
Okay. Okay, so this is the last question. Then we will take some questions from the next question paper. Okay. Which of the following approaches uses the full attention mechanism during inference with the attention complexity OT at the time t is equal to t? So we had seen that full attention, if we do full attention, then it is OT square, OT square D. Okay, and we had also seen in the lecture that when we do multi-query attention and group query attention, multi-query means that KV value which is there, it is cached in the memory, and then it is shared all across all the heads. Okay? All the heads. And that time your computation becomes OT because you are not doing every time. Similarly, for the group query attention also it becomes OT. And paged attention is like if you have studied like your operating systems in OS, there is something concept called contiguous memory and uncontiguous memory. So what happens? He has got pages, and these pages sizes which are there, they keep on decreasing and increasing. So the memory which you are allotting for KV is not fixed here, because in some cases you don't require that much of memory. So in all the three cases, your complexity is OT in this case. Is that okay? This you can go through the lecture. Okay? Professor has not explained this part. Okay? He explained these two parts. This page attention. Okay? Any computer science student, he will recollect. Okay? It is coming from OS. Okay. So with this, okay, this paper is finished. Shall we see the other paper also? Some 2-3 questions from that. They are different. Which are different?
Yes.
Sure.
Yeah. So this is afternoon. So we go to forenoon question paper and see if there are some different questions in this. Where is it? Okay. So in this, okay, they have asked for the BERT. Okay. So please remember the full forms of GPT, BERT, BART, T5, C4 in case okay, they asked. Okay. The statement that, okay, this is a question, different question. So we will include in this document. I'll share okay, after this session. So the statement that in general, position information can also be injected into the attention layers of a transformer model instead of the embeddings of the input token is true. We have seen that. We had seen that, no, that at during the attention time, we inject this Pij, which is there, Xi into WQ into WK transpose into Xj plus Pij. So we can inject during attention score also, and that's why this statement is true. This question is same. This question is same, and see here, okay, they have given the correct answer. Here it is B. Okay. Yeah. Now this question is same. The use.
Lalit, please, can you please go back to the yeah.
Yes.
So, so in this question, why I am wondering why y12 is not the correct answer.
Okay, so just check again. First of all, let's check that what is the question.
It's the same question, I think.
No, that question was the summarization task.
It is on the summarization of it.
T was 2048 last time.
Yeah, it is just 1024 this time.
Yeah.
Yes. So
Please.
now,
5. Why not 512? Yeah, that's the question.
yeah, you're right. Okay, as per me also 512 should be there. Only 1024 should not be there. It is the same task, text summarization. You are doing with 1024, so it will have less than 1023. User runs inference on the model n times with an input size contains 712 tokens, special token. So this also should be correct. Okay, only this should be wrong.
I was wondering whether it has something to do with the inference mode or something.
That there also it was the inference, na?
Yeah, that's why.
It was doing the inference only. It is only that how many tokens it can generate. The question is that only. So in case you are training with 1024, it will generate only 1023 because the last token is your end. This is there. Okay. This question is same. This question is same. In this question, okay, they have got a extra question. So let's do this also. So vocabulary remains same here. And they have asked for this. And they had mentioned not to take W. Okay, so again, okay, we do the same 1 0 0 0 0 0 0, And in the first pass, okay, what will happen?
10.
First pass only 10 will come. So 1 0 0 0 0 0 0. So 1 2 3 4 5 6. So 6 tokens. Okay, let's check the answer. So it is 6 only. This question is same, okay, calculation question. Number of encoder layers same, okay, 2566. Same question. This is also the same question. In this only they have asked, okay, for the coffee. So instead of often, they have asked for coffee.
Yeah.
Yes. So for coffee, what we have to do? Let's go to that question. So for coffee, what we'll do? We will find, okay, we'll do the multiplication of this row. This will come from here. Is that okay? This will multiply by V and here, and we'll get two values. So we'll get for the coffee. Now next one is, this is same coffee with much. So same concept, it remains the same. There is no change. This question is same. This is same. They are equal. And zero based indexing, this is also same. So all questions are same. Now anyone with any doubt about the GA questions, okay, we can discuss that before we close this. Hi Anant.
Hello.
Hi. Any discussion anyone wants to do about any GA question? Any doubt lingering in the mind about any GA question?
Not as of now.
Okay. So I think while discussing the PYQs, we have gone through the concepts also. If somebody wants to have
Yeah.
any, yes.
Could you do GA11 ones? Just GA11, that's all. GA11 में question number.
Okay, GA11, na?
Yeah, M flops and how to calculate this.
Okay. GA11 graded assignment. This one a question? This one?
Yeah.
First question. Okay, so we don't have to remember any formula for all these questions. T is equal to 124, D model is 512, DQ, DK, D model, one flop for a single mathematical operation such as addition and multiplication. Now calculate the exact number of flops, floating point operations required to compute the pre-attention scores. Enter your answer in M flops. So when we compute the pre-attention score, formula is Q into KV.
Yeah.
And Q dimension is T into D, and this is D into DT. So here your complexity is OT square D, but number of multiplications which are there, it is T square D, number of multiplications.
Yeah.
And number of additions is equal to T square D minus 1. So your number of flops will be T square D plus T square D minus 1. So this becomes 1024 into 1024 into 512 plus 1024 into 1024 into 511. This becomes 1024 into 1024 into 1023. Okay. So these are the number of flops now. Okay. So addition and this is. And any other thing they have given, this is their number of flops. Okay. So now you have to answer in the M flops. Okay. So for M flops, okay, you will do 10 to the power 6. Okay. Divide by 10 to the power 6.
Got it. Okay, got it.
Okay.
Also, what will be happening at attention? What will be the number of flops at attention if you want to calculate that?
So Okay, so they asked okay, at only this okay, at the time of computation
Potential.
of the attention score only. Okay. Otherwise, if you want to calculate, for Q also, for K also, then for K, Q is the multiplication between your input layer. Input layer will be your T, length of T, okay, which is there,
Mm.
T into D into D into D.
Yes.
So here number of multiplications will be T into D, which is TD square.
Yeah.
Number of additions will be T into D minus 1.
Got it.
Okay, so then you add, okay, this is for Q, and for K also will be same. So this will be TD square plus T into D minus 1. So these
Mm.
are the number of flops, okay, for Q and K. Okay, and
Got
QK,
it.
T we have already calculated that this is T square D into plus T square D minus 1. So if they
And
ask
what
for all, then we can calculate this.
and
Z
Z would be also same.
Z is calculated thereafter if you ask for the full representation.
Mm.
Okay, so till attention score is this much. Till attention score is this much. Now, before after this, you do the softmax also.
Mm.
So for softmax also, how many operations will be there? It is again T square D is there, okay, that for everything you are calculating softmax.
Mm.
Okay. And for representation, now you multiply this T into T into T into D. So
Yeah.
your number of multiplications will be again T square D, and number of additions will be T square D minus 1. Sorry, T into D into T minus 1.
Mm.
Okay, so then again, if you want to calculate for the entire, so these are the components for that. But in this question, they had asked only about attention score.
Yeah, I just wanted to extrapolate on that.
Yes. Any other question? This question already they have clarified. Okay, this answer is correct. Okay, 2097.15.
For this, okay.
This question I have explained how to solve it quickly. Just it is a child's game. There is no problem.
So basically, in this question, you have to see if there's any block that
Yes,
column name.
yes. What we have to see the block which is there. Okay, I'll copy from here only. Immediately we can come to know from these blocks. See, this is
Mm.
Q2, this is Q1, this is Q1, Q2, Q3, Q4. These are
Got it.
Ks. This is K1, K2, K3, K4. So this is Q1, K2, this is
Yeah.
Q2, K3, this is Q3, K1, and this is Q4, K4. So this is how you write it here. And if they tell you in the form of pi, for example, they tell you 2013. So this is nothing but this is the K value. K3, K1, K2, K4, and it will interact with Q1, Q2, Q3, Q4. So it means as per this specification, Q1 will attend to K3, Q2 to K1, Q3 to K2, and Q4 to K4. Okay, this is how you.
Got it.
Yeah. Any other doubt, lingering doubt, any discussion okay, anybody wants to have?
Yeah, and so in the PYQ question about the parameter calculation, so 256 is the right answer or the wrong answer in the PYQ?
256 का D embed is I think we can take as a walkup size.
Vocab size.
Yes.
So so what is the vocab size? I mean, it was not given, right?
So just hold on. Can we take?
Maybe.
Just hold on. Ask our alma mater क्या है ना? D embed as lookup size. Okay. Yeah. Yes, we can use the vocabulary size as the embedding dimension in certain scenarios.
Good.
Okay. Yeah.
So you're getting the same answer. I am asking the answer was matching or not?
Answer is matching. Okay. I had calculated. I'll just show you my answer. Okay. I had calculated it. I'll just share with you. Quantum division LLM. There. This document I'll share with all of you. It has got all the concepts, also week-wise concepts. Just go to GAs also. This क्या अपना somebody had just during this session only somebody had told that it was a correct this. Can we do the calculation again क्या of these parameters?
Sure.
Yeah. Where is it? Where is it? Here. Okay. Okay. So we do it. Okay. So we take for embedding layer and the output layer is the same. Output layer is same. Is 256 into 256. Can somebody calculate this and can keep on giving? We can make. Then we do MHA. MHA is equal to 4 into 256 into 256. Then we take the layer after MHA. This is 2 into 256. Then we go to FFN and they have said with the bias. And FFN is 1024. So this will become 2 into 1024 into 256 plus 1024 plus 256. Then layer of FFN is 2 into 256. Anything else that we have forgotten? Anything? Model fixed position. So 256 into 256 is
65536. 536.
Okay. This one?
I've covered the entire thing in one go. Sorry.
Just 256 into 256 is.
I'm telling you.
Yeah, okay.
It's 2,62,144.
2 to power 56, na?
It's 2,62,144. I don't know what would be the power.
Okay, just hold on. This is 65536 is correct. Okay? Let's obviate any mistake. Okay? 65536. This will become into 4. Same. Into 4. 262144. 262144. This will become 512. This will become how much? 2 into 1024 into 256 plus 1024 plus 256. 525568. 525568. And this is 512. This becomes 1024. 525568.
Eight lakh 54,272.
1417 613 to 14. This one 854272.
Yes.
Now we have got 3 layers. Okay, so we have 3 to just 6, 3 7 just 21, 3 to just 16, 8, 3 4
2,
just
5, 6, 2, 8, 1, 6.
15, 116, 3 to 24, 3 4 3 कितना 2 5?
2, 5, 6, 2, 8, 1, 6.
This is the Anant ke, this is the answer that we are getting.
Okay. So there is a actually difference of 4,000 actually here. The given answer was 2566.
This is a let's check.
Yeah.
So can we
There's difference of 4,000.
I guess we're adding more D models. Oh, sorry, layer norm mein, it should be only D model plus D model.
No, then it will reduce, na? Answer they have given 2566.
Yeah.
Answer they have given 2566. Now let's just go through the question again. There might be some googly here. So there is a encoder layer of the vanilla transformer. Okay, encoder layer of the vanilla transformer. Okay, with the following configurations: context length T, D embed which we are taking V walkup size, D model 256. This does not matter to us here. 38 into 2 becomes 256. DFF is 1024. The parameters in the feed-forward neural network comprise both weights and biases, which we have considered here. The model uses APE with fixed here. There is nothing. N is equal to 3. What is the total number of learnable parameters, including the parameters of the input and position embedding layers in the model? Enter the final answer in thousands. So they have given 2566. Okay, 4,000 difference is there. Okay,
Yeah.
so let's say all of us deliberate more and maybe we will ask on the discourse then.
Okay.
Because as per me, the answer should be this, because we have not forgotten any step in this.
Yeah, and what I'm guessing here is maybe there's a difference of number 4096, I guess.
4096.
Yeah, I am thinking that probably should be the difference.
4096 is 64
Yeah.
into 64.
Yeah, probably yes. It's 64 into 64.
But from where it will come?
Yeah, that's what I'm saying. If you want to convert 256, then it will 256 into 16, I guess.
So there is some catch here. Either if we increase the walkup size to, instead of 256, if we increase to 1024, that will also make a difference.
Yes.
Okay. So there is some catch again. Okay. I will flag it on the discourse again, and I'll share the link on WhatsApp again. So all of us we flag it again.
Sure.
Yeah. Any other thing? Any addition, subtraction from anybody? Hi, Abhi. Okay. So we call it off for today.
Yeah.
And in case of any new thing, we'll collaborate on WhatsApp then.
No worries, sir.
Yeah. Okay. Thank you. Thank you.
Thank you, sir. Thank you for your time.
Thank you.
Yeah. Okay. Have a nice day. Bye bye.
Okay.